All right, so we're here. I've got a mechanics and materials problem. This is a rigid beam ACE that's suspended by three bars. Each bar has the same length L, and the bars are made of the same material, meaning that they all have the same modulus of elasticity E, and have the same cross-sectional area. So the first thing we're going to do is draw a free body diagram of this. So draw free body diagram, and this free body diagram would be here. I have my beam ACE. Here I have some draw my tension forces associated with each rod here. I'll call that NEF, NCD, and NAB. And then I have the external load applied here, P here. And I would look at this and I see already that this is what is called statically indeterminate. Statically indeterminate. And the reason it's statically indeterminate is because I have one, two, three unknowns, but only two equilibrium equations that are going to be. So my number of reactions is greater than my number of equilibrium equations. The number of equilibrium equations I have available here are only two. The only two I have available to me are the sum of the forces in the y and sum of the moments about a point. Okay, and so if I did sum of the forces in the y equal to 0, this would be NAB plus NCD plus NEF minus P equals 0. And if I take sum of the moments about point A, which is over here, take moments about A, this would just equal to 0. And I would have here, I would have, let's see, NEF times 2D plus NCD times D minus P times D over 2 equal to 0. Okay, and here you can see, and if I tried sum of the forces in the x equal to 0, right here, this is useless. It tells me nothing. Okay, so that's why I only have two equilibrium equations. I have three unknowns, or three reactions, if you will, and and uh, um, and two equilibrium equations. All right, so I see here that my unknowns are NAB, NCD, and NEF. So that's right here, and I can see them again here. So I have NAB, NCD, and NEF, NEF, NCD. Let's do the same right here. Okay, so I need another equation. That other equation is going to come from a compatibility relationship. Okay, or a kinematic relationship. Okay, so here, compatibility or kinematic equation. Kinematic equation just means some relationship with respect to its deformation. Okay, and when I apply this load P here, what's going to happen if I have initially here, let's say this is point A, here is point C, and here is point E, right here. This whole thing is going to move down a little bit. This end right here is going to move down maybe a distance over here, E. This can be delta E. And then I'm going to have, I'm going to have more, if you will, if you look at this, I'm going to have more deflection where my load is. So at point A, I'm going to have the most deflection. Okay, it's essentially going to be a trapezoid here. Okay, and here would be my new C. So this might be like A prime, C prime. And this would be delta C, and this would be delta A, delta A. Okay, and what I want to do is relate all three of these deformations together. All right, so to get my other equation. So when I look at this right here, when I look at this, I want to use similar triangles. And if I look over here, if I just do a straight line across, oh, that's not the best drawing in the world, but here, this motion right here, that location right there is delta C minus delta E, and this right here is delta A minus delta E. And if I use from similar triangles, okay, I would have here, and I know before this is a distance D, and this is also a distance D, okay? These are all distances D. From similar triangles, I have delta A minus delta E over 2D is equal to delta C minus delta E over D, all right? And so here, just from this relationship, so what I have, if I look, the D's cancel out, done. Okay, 2 right here, if I just multiply this across, I have delta A minus delta E is equal to 2 times delta C minus 2 times delta E. I'm going to add that delta E over there. I have delta A is equal to 2 delta C minus delta E. Okay, and then if I substitute the definition of the axial deformation of each rod, that's, that equation, delta is equal to NL over EA. I would have here NABL over AB over EAAB is equal to 2 times N CD LCD over EACD minus NEF LEF over EAEF, okay, over EAEF. And all the areas are the same, all the modulus of elasticities are the same, so I can just cross these out because I have the same material, same length, same cross-sectional area. In this equation, I'm just left with NAB is equal to 2NCD minus NEF. And I will leave it to you because now I have my third equation, and for all three unknowns. So here, this is my other unknown. NCD is here, and this is a square right here. So I have three equations: 1, 2, and 3. And you can calculate the normal force for each of those, and then just plug into sigma is equal to N over A. So whatever the normal force is divided by A, and you got the normal stress in each rod. All right, all right, sweet. That was under 7 minutes.